Hey there, college algebra folks, back here with another video covering some practice, primarily from section 5.3 material here. We might see a little bit towards the end get into 5.4 material, but right now I think that most of this is primarily from 5.3, a lot of this material, where what we are looking at here, what we are taking note on in this section is we are starting to look at logarithms. All right. Particularly, we're introducing the logarithmic function, but there's a lot that comes along with logarithms. The first idea being, where do they come from, right? What is a logarithm in a sense, right? These can be very what we might not be very familiar with what we mean by a logarithmic value, right? And where logarithms come from is this idea of the inverse of a function, right? We introduced last time functions that look like this. This is known as an exponential function. And what we had introduced here, right, when we considered this exponential function, it's going to have a graph that looks like one of two things. It's either going to be a graph that illustrates exponential growth, or it's going to be a graph that illustrates exponential decay. Now, either one of those two graphs that we consider in this case, right, either the graph for right, exponential growth, which might look like that, or the graph for exponential decay, which would essentially reflect that graph around the y-axis, might look like that, where in either of those cases, right, both of those graphs not only illustrate functional behavior, they pass a vertical line test, but they also exhibit what we call one-to-one behavior, right? They pass what we might say is the horizontal line test. Every exponential function in the form here, f of x equals b raised to the x power, right, passes the horizontal line test, right? So it, what does that tell us? Must be one-to-one, and f inverse of x must exist. There must exist this inverse function, right? And where does that idea of this inverse come about from, right? Is if we actually then start to think about, right, the case for f of x equal to b to the x, right? And we say here, find f inverse of x. If we remember our process there, we learned this back in section 5.1, just 2 sections ago. We are going to replace the f of x with the value of y, right? So that we make the equation y equals b to the x power. We then swap our x and y values. We swap their locations inside the equation. So we make this y into an x and this x into a y, right? And then we solve for y. Right? We're going to have to solve this equation for a y. And I'll give you a moment to think about that. Again, how do we solve that for a y? And I do have students come along and they say, well, we can take the yth root on each side. Wouldn't that work? And that would solve for the value of b, right? But it's not actually going to solve for the value of y. Right? And this may be a bit of a puzzle to you because really we haven't discussed, or really might not be very familiar with, the behavior that would be necessary here to solve for y. And mathematicians ages ago had the very same question about exponential function. They said, how do we solve this for y? How do we get this y all by itself, this power, on one side of the equal sign? And they said, well, what we may need to do is we may need to devise a new type of functional behavior, right? And we may all have to agree upon this new type of functional behavior. And that what they established was the following idea, and that is that x equals b to the y if and only if we can rewrite this as saying y is equal to the log base b of x, right? We established, right, this understanding that if we have this statement here and we want to solve for this y value here, right, solve for this y value in the power, to get that y value all by itself on one side of the equal sign, we need to think of this relationship as being what's called a logarithmic relationship, right? And they gave it this name known as a logarithm, right? And what that allows us to do, right, is if we go up here above and we're now solving this for y, right? Well, y is just going to be equal to the log base b of x. Or there we've solved for y. It's really a one-step process if we establish this understanding. And we know in our process of finding inverses then, if we're looking to find this inverse up here, right, we're just going to replace now the y with our inverse notation. Once we have solved for y, we have this inverse notation, and what we're able to say is f inverse of x equal to log base b of x is the inverse of f of x equals b to the x, right? They are what we call in an inverse relationship with one another, right? We could take this just a step further to look at one quick specific example before we dive into some practice here, right? So if we considered something like f of x equals 4 raised to the x power, right? From this understanding, right, if we actually put ourselves into the process of solving this, right, for an inverse, and we said something like find f inverse of x, right, we would find f inverse of x by letting f of x equal y, interchange the location of x and y in that equation, and then I'm going to solve for y. And how do I solve that for y? Well, we understand x equals b to the y if and only if y equals the log base b of x. So we say this is true if and only if. IFF is a quick abbreviation of that statement, if and only if. X equals 4 to the y if and only if y equals the log base 4 of x. Right? That is the application of this understanding for logarithms, this fundamental relationship between exponential and logarithmic functions. The fundamental relationship there being they are the inverses of one another. Right? What we're able to say then here is f inverse of x must be then the log base 4 of x, right? And f inverse of x equals this for the case of f of x being just 4 to the x power. These functions are inverse relationships with one another, right? What does that mean is if we compose them with each other, right? If I took f and composed it with f inverse in this case, add x, that would be plugging into this power of x, the log base 4 of x. If I took 4 and raised it to the log base 4 of x power, that log and the power cancel, leaving you just with the value of x. Right? Or if I considered doing that, right? If I considered doing that in the other order of composition, f inverse composed with f at x, right? That would be plugging this function into the other for x. That would be like finding the log base 4 of 4 to the x power. And the log of base 4 cancels with the power of base 4, which gives us back just the value of x. These are inverses of each other. So we can use that to answer some questions here in our examples. All right? The first few problems are rather quick here. Express these exponentials as logarithmic statements. Well, that all goes back to this statement right here. X equals b to the y if and only if y equals the log base b of x. What you will notice in this statement is b plays the same role in each statement. That's the base. What happens, though, inside the equation is you get one of the variables all by itself on the equal sign, on one side of the equal sign, where if you have this exponent here in the exponential, it becomes by itself in the logarithm, and the argument that it was equal to in the exponential becomes the argument of the logarithm, and vice versa. So if we look at a statement like z equals 4 to the p, z equals 4 to the p, if and only if what has to be true, that power p is equal to a log base 4 of this value z. Right? And there's our corresponding logarithmic statement. Or if we see s equals 9 to the t, that is true if and only if our power of t is equal to a log base b of 9 applied to an argument of s. Right? That is all we're looking at in these first few examples, is just applying this fundamental understanding. And what this if and only if means, folks, is that this goes back and forth. This means this. Well, I should say, this means if and only if this means this. Right? And this means this if and only if this means this. The statement if and only if implies these ideas go back and forth. So I can use that same idea here. R equals the log base 5 of Q if and only if, right? This argument of x inside the log would be set equal, well, on one side of the equation all by itself, equal to our base b, just being the base b of our exponential statement, and then whatever was equal to itself all by itself on one side of the equal sign here becomes the power on that base of b. If we apply that here, that means this argument of the log, q, must equal the base of our logarithm raised to this power of r. Right? Or here, u equals the log base v of w, if and only if that argument of the log, w, equals the base of the logarithm, which is variable now v, where that v would be raised to this power of u. Right? That would be the corresponding exponential statement in that case. Right? And we can apply those ideas down here to find our inverses. If we consider finding the inverses of these, and actually what I might do here is, these might take a little more paper, so let me bring these out here. Fold this over here. Let me fold this over here. And we'll do that fold one more time. We'll bring this up like this. Get it in there. All right. And we'll consider answering these questions, right? Consider finding the inverse of this exponential function right here. All right. As we know, y would be equal to 1/2 times 5 raised to the power of x plus 2. We then swap the locations of x and y. X must be equal to 1/2 times 5 raised to the power of y plus 2. And now we must solve for y. First thing we would do to solve for y is we might multiply both sides of the equation by 2. That will give us just 2x on the left, but it will cancel that 1/2 in front of the 5 times. well, in front of that 5 raised to the y plus 2 power. That will leave just 5 raised to the y plus 2 power on the right. Now, we're trying to isolate this value of y. We're solving for it. So how do we isolate that value of y? Is we now apply this idea. This exponent can be rewritten into a corresponding exponent or logarithmic statement. The power seen here, y plus 2, must be equal to a logarithm where we have the same base as we see in the exponential being now applied to what was all by itself on one side of the equal sign here, that value 2x. And then from there, we're solving for y. We just now subtract 2 from both sides. Take 2 away from the left, take 2 away from the right. You will cancel the 2's on the left, leaving you y. And on the right, you will have the log base 5 of 2x minus 2. Right? And what is this? Since we have solved for y, that is our inverse function. In this case, again, the inverse of a exponential, right? The inverse of this exponential is this logarithmic statement. Right? And notice we should start to see inverse behavior here, right? What's the inverse of multiplying by 2? Dividing by it. Right? What's the inverse of subtracting 2? Adding 2. And what's the inverse of raising to an exponential power of base 5? Is a logarithm of base 5. Right? And notice the order in which those are happening. This is inside the function, this is outside. This is inside the function, this is outside. Right? There's that inverse order of behavior. All right? If we look at B real quick, right? Here we have f of x equals 5 minus 2 log 3 base 3 of x plus 2, right? So if we start finding our inverse, we first make the f of x y, 5 minus 2 log base 3 of x plus 2. We then interchange the x and y's values and location inside this equation. So this would become x equal to 5 minus log base 3 of y plus 2. And then we start to solve for y. First step in solving for y is we move this 5 from the right to the left by subtracting 5 on both sides. Right? That will leave us with x minus 5 on the left, and the minusing 5 from the plus 5 out front here would leave minus 2 log base 3 of y plus 2. All right? Next step in solving for this y is get rid of this factor and negative 2 out in front, this constant multiple. I'm going to get rid of that by multiplying both sides by negative 1/2. Right? That might produce, if we distribute everything here or put this over a common denominator, we might say this is going to turn into 5 minus x with the negative distributing all over 2, right? The 2 moving to the denominator here, must be equal to, and we would have this negative 2 and negative 1/2 cancel on the right, what's going to be the log base 3 of y plus 2. Where now how do I isolate the y inside this logarithm? Is I go back to this fundamental understanding. Right? And this means this is true if and only if 3 raised to this power, 5 minus x divided by 2 on the left, is equal to, on the right, what would be left behind is just the quantity y plus 2. Where we can see here to finish solving for y, we're just going to subtract 2 from now both sides. And we will be left with, if we rearrange that, y equals 3 raised to the power of 5 minus x divided by 2, all minus 2 in value. And that would become what we might say is the description of our inverse function. Right? F's inverse is 3 raised to the power of 5 minus x divided by 2 minus the quantity 2. That is the inverse, if we take note, of this function up here. Right? And it was just found using our process of finding inverses, folks. Right? It was just found by, as we said, making the f of x, y, interchanging the x and y in the equation, and then starting a solution process, solving for that value of y. In that process, you are going to have to either convert an exponential to a logarithm or a logarithm to an exponential statement, where you are going to have to rely on those fundamental skills, right, that come from that understanding of what it means to be a logarithm, folks. Right? So I do have a couple more examples I want to come back and look at. You can see here we're going to be doing some graphing. We got to actually establish the logarithmic function and so forth, and work through a couple more examples, but I'll be back to do that in just a moment. Hey there, college algebra folks, back here with a few more examples of material from section 5.3. We're looking here at the logarithmic function, looking at a study of logarithms, where through the what we had noted was this understanding of what is a logarithm. We did establish this idea right here. We did establish what is a very a new type of function, a function that we wanted to add to our library of functions. Right? In a sense, in our library of functions, we do have now the case for a logarithmic function. In our library of functions, where that logarithmic function takes on the form f of x equals the log base b of x. And again, b is known as the base, right? It's called the base of the log, or the base of the logarithm. Again, b has to be greater than 0, and b is not allowed to be the value of 1. Right? When in order to have what we call logarithmic behavior illustrated. Right? Now, we could start to think about making a table of values for this logarithm in terms of what would be some common x and f of x values. And what we take note on, again, we go back to this idea that these two functions are inverses of each other. Right? And this function b of x, we knew that if we made a table of values for b of x, that we would pass through a couple of common or easy to find points. Those would be the coordinates 0, 1, 1, b, -1, 1 over b in value. And we had seen that in our last examples, set of examples, the video before this, right? Where if we now think about the relationship of the exponential function being the inverse of a logarithmic function, we understand that there's a corresponding relationship between the values that we see in this table here, right? That being an inverse relationship to values we will see down here in the table or in the graph for the logarithm. And a log base b of x will pass through the three common points, 1, 0, b comma 1, and 1 over b comma -1. Right? And if it's the case that b is greater than 0, what you will see happen graphically is you will get a graph that illustrates logarithmic growth. Or if b is less than 0, we will see a graph that illustrates what we understand is logarithmic decay. Right? And we would see those common points right here. This would be the point 1, 0 that would occur in both graphs. Right? Out here you would have this coordinate that would be located at b comma 1. Right? 1 occurring along the y-axis. That would be that would be in this graph. Well, careful, b would be fractional in this case. It'd be not less than 0. Let's be careful there. B would be less than 1 greater than 0 is when we have that decay. That's why I'm getting turned around here. Where certainly when we would be at a b that was fractional between 0 and 1, we would be up here at 1. Right? That would be at the coordinate b comma 1. And when b was between 0 and 1 and we took the reciprocal of it, we would be down here at -1 on our graph. Right? At this coordinate 1 over b comma -1. Yes, and that would be this corresponding point back here. This would be at the coordinate 1 over b comma -1 in value, right? Happening there on our y-axis. All right? So what we take note on is that in a logarithmic function, we will see these 3 common points. And we want to basically store away this information into our library of functions. We want to have this fundamental understanding for a logarithmic function. So that if I face something like having to sketch their graphs, all right, in this first case, if I want to consider sketching the graph of the log base 5 of x, right? Oh, one other idea I should have pointed out about these graphs, and this is going to be also important. Before I go on, keep in mind also the vertical asymptote. Well, the x-axis, not the x, the y-axis here is going to play the role of a vertical asymptote. Right where x equals 0, you will have a vertical asymptote. What we do have here in the logarithmic function is we do have a domain concern, right? That is, this value of x has to be greater than 0 in value. You see that behavior in this graph. The points always fall for values of x that are greater than 0, and you see the same thing here in this graph. At x equal to 0 in both graphs, you have a vertical asymptote. So as x approaches, or the graph approaches that asymptote, it's either going to head down towards -infinity in the case for growth, or it's going to head up towards +infinity in the case for logarithmic decay. All right? And you do have this domain concern. This value on the inside here of your logarithm function has to be greater than 0, that argument. And I just point that out here before we jump into graphing, because that is a big point in these graphs, right? This is what we think of as being a bit of end behavior, right, in this logarithmic behavior overall. If we start with this first case, log base 5 of x, that's a fundamental form where we can note b is just equal to 5. So that tells us there are 3 common points we pass through. That's 1, 0, 5, 1, and 1 over 5, -1 in value. We will find those 3 points in our graph. And in this graph, you will have that x-axis play the role of a vertical, or that y-axis where x equals 0 play the role of a vertical asymptote. We will pass through this point right here at 1, 0. We will also pass through the point out here at 5, 1. Right? That's these 2 points. And we will pass through this point back here at 1/5, -1 in value. And if we go back to what would be the shape of this graph, right? If we go back to my notes on shape of this graph, right? Since b is bigger than 0, we're going to see this logarithmic growth occurring. We're going to have an n that starts down here at -infinity along this vertical asymptote, comes up and passes through those 3 points, illustrating this logarithmic growth, folks. All right? And you do notice this x has to be bigger than 0. All right? If I apply that understanding here, you will note we have some transformations here. This resembles f of x equals the log base 1/3 of x. What does that mean? Well, here we have a b value that equals 1/3. It's going to look a lot like the case we would have for, since b is a value between 0 and 1, we're going to have the case for this logarithmic decay. Right? We would see something that looks a lot like, again, we're going to have a vertical asymptote where b equals 1, well, at x equal to 0 along this y-axis, and we will pass through a couple of quick and easy to find points. Those being those 3 points right there. What are those 3 points? This is 3, -1. This is 1, 0. This is 1/3, comma, +1. All right? It's those 3 values that we're guaranteed to have in this graph, right? 1, 0, b1, and 1 over b, -1 in value. All right? Well, the graph of this looks a lot like this graph, except we have a few transformations. Now, if we break that down, right, those transformations, we've done this a couple of times, we do have the case for A, B, C, and D here. And in a logarithm, what you really want to pair that up with, perhaps, is maybe you have g of x equals a times the log base little b of the quantity big Bx plus c in parentheses, all plus d. Where if we pair that up with this up here, we can see that the values of 2 and 4 align with these values of big B and big C. As for the value of A, in this case, it is the value of 1. And as for what we're adding on at the end back here, right, we're adding on nothing. The only values we have are B and C, right? Now B, remember, that's our horizontal compression. And if we took C over B, right, that would be 4 over 2. That would be 2. That's our horizontal shift. Right? This tells me I have to shift, because it's positive, left 2 units. And this tells me I have to compress, right, because I'm greater than 1. So I would compress by a factor of 1/2. And where all that affects are these coordinates, or I should say the x values in these coordinates, right? I do have to translate the points on this graph, right? What we are going to translate over here are the points on this graph, which we could go back and note were 1/3, 1, 1, 0, 3, -1, over to points in what would be the graph of my transformed function. I called this f of x. Let's just renote it as g here, and we'll call it g of x down here. All right? Where I'm going to take these x coordinates, I'm going to have to first multiply them by 1/2, the reciprocal of b. All right? So they are going to be multiplied by 1/2, and then subtract 2. X is going to have to be times 1/2, and then minus 2. So 1/3 times 1/2 is 1/6, right? And minus 2 from 1/6 is going to leave us -1 and 5/6 in values. Our g of x, the y coordinate doesn't change. There's no vertical transformations happening here, just the horizontal ones. Take 1 times 1/2 is 1/2, and subtract 2, you get -1 1/2. And that's going to have a y coordinate at 0, right? Because this y coordinate doesn't change, right, from our transformations. And then lastly, we divide this by 2, or multiply this by 1/2. It's 3/2, and if you subtract 2 from that, you get -1/2. Right? So that would leave us at the coordinate -1/2, comma, -1. And if we plot out these points in our graph, right, we will see this behavior where the graph will shift left 2 units and be horizontally compressed by 1/2, right? It'll be smashed down horizontally by 1/2, right? So now, along with that, we'll also shift left 2 units and be compressed, is that vertical asymptote. So what I'm going to do in my graph, first of all, is shift and compress that vertical asymptote, which really just is shifting it left 2 units. And then that's going to help me align these points, right? -1, 1/2 is going to be this location right here. -1 and 5, 6, 1 might be this location right here. And -1/2, -1, right? Remember, this is -1, -1/2 might be right here. That's going to be my graph that's illustrating this logarithmic decay. And its graph is going to look very similar to this, except it's going to be smushed horizontally and shifted left 2 units. And coming down from that vertical asymptote and passing through those points, we might sketch that as the graph of this logarithmic function. All right? So folks, we do want to familiarize ourselves with the logarithmic function, right? And we want to understand what that means by what it means to be a logarithmic behavior, right? To either be what we call logarithmic growth or what it means to be logarithmic decay in behavior, right? And we are basing all of this on the idea that we're just the inverse of an exponential, right? And all logarithmic behavior illustrates is the inverse of exponential behavior. Folks, I do have to come back and talk a little bit more about logarithms in terms of evaluating them, and then in terms of working with some of their properties. So we'll come back to that here in our next video. See you then, or in our next section of this video. See you then. Hey there, college algebra folks. Wanted to come back, work a couple more examples from this section 5.3 material where we're studying the case for the logarithmic function, where keep in mind what we have established is essentially this, what we think of as inverse relationship to exponential behavior, known as logarithmic behavior, that is given or described in this function known as a logarithmic function, where what we want to add to our library of functions is this function here, f of x, equal to the log base b to the x, this fundamental form, right? Where with respect to this fundamental form we want to put in our library, to begin with, the value of b is known as the base again, the base of the logarithm. B has to be greater than 0 and b cannot equal 1. Right? And with respect to its graph is given by either the case where we see logarithmic growth, where b is greater than 0, or the case where we see logarithmic decay, the case where b is between 0 and 1 in value, right? And in either of these graphs, they all pass through 3 easy to find coordinates, those given by the coordinates 1, 0, b1, and 1 over b, -1 in value. All right, those values, those 3 coordinates given in general for this fundamental form will describe one of these 2 graphs, depending on what is our value for b in the base of that logarithmic function. The other important aspect of these graphs to go back and keep in mind is that they did have a vertical asymptote in them given by the y-axis, where the graph is either heading down the y-axis towards -infinity in the case for growth, or heading up the y-axis towards +infinity in the case for decay, which did leave us with some domain concerns. The other thing we are adding to is our list of domain concerns. The argument inside of a logarithm always has to be bigger than 0. And we may actually start there with our next questions here. These are the questions we see going along in number 5. In number 5, we are given these two logarithmic functions, right? They fit this fundamental form. They are a transformation of this fundamental form. But what we need to take note of when we're questioning domain in these, right? Determine the domain of these functions, is we need to watch that argument that the logarithm is being applied to. That argument has to be greater than or equal to the value of 0. So in this first case, that argument is described by 32 minus 8x. 32 minus 8x must be greater than 0 in our domain, which does imply that if we subtract 32 from both sides, negative 8x would be greater than negative 32. And now when I divide in my next step by negative 8 on both sides, I will end up with an x on the left-hand side, but because I'm dividing by a negative, I do want to switch the direction of my sign and make the statement that x here has to be less than the value of 4 found on the right-hand side. All right, here is my domain description. If this is my number line for x, and this is the value of 4 on my number line, x must be everything less than 4. We can include 4. We can get really close to it, but we don't include it. And we are every value from negative infinity up to the value of 4. So in some interval notation, we might write that as this interval negative infinity to negative 4 in value. Whereas in this particular case, right, in this case of this logarithmic function, we have a different argument, but the same condition. That argument, 1/2 x plus 10, must be greater than 0, which means 1/2 x must be greater than negative 10, or in our next step, we would just multiply by 2 on both sides, which does not change the direction of our sign, and we end up with the statement x must be greater than negative 20. If this is our number line for x, and this is the location of negative 20 on that number line, we can be everything very close to negative 20, but not equal to it, all the way up towards positive infinity. This interval is from negative 20 to positive infinity in its description. All right, so one thing we will keep in mind is that the logarithmic functions do bring up domain concerns. We do have to watch that value inside the argument of a logarithm. It always must be greater than the value of 0. And to find those domains, respectively, for a given logarithmic function, we just set that argument greater than 0 in either case. Now, we might back up and look at this question here real quick. In this particular case, we're asking ourselves to evaluate different values of this function. We know the value of the function at 3 very specific values of x, but what if I was to add in other values here for x? What if I was to look at the number 2 or the number 3 for x? What would that result in terms of the value of this logarithm? All right, we do need to be able to at times evaluate a logarithm. Right, determine the value of a logarithm, a skill that we still have to here develop. All right, and what we rely on in developing that skill, we go back to our understanding here that these are inverse behavior. When we think about the log base 2 of 125, oh, careful, that's not 2, that is 5. Right, log base 5 of 125. We are trying to figure out what that equals. That in a sense is an unknown value. We might call that the unknown value of x. Right? And we know that the log base 5 of 125 equals x if and only if what's true, well, that would be that 5 raised to the power of x would be equal to 125. Implying, if we think about it, 5 to the x power would be equal to 5 to the third power, right? Or that when we think about that value of x would be equal to the value of 3. The log base 5 of 125 is just the value of 3, right? That unknown value is just the value of 3. When we look at a logarithm, we are asking ourselves, when we're trying to evaluate this logarithm, we are asking ourselves, what power do I have to raise this base to? What power do I have to raise that base to so that the result equals 125 in this case, or equals the result found inside of the logarithm? So we're really asking ourselves, 5 to what power of x equals 125 when I'm asking about the log base 5 of 125. All right? The log base 5 of 125, well, that's just equal to 3 in this particular case. All right? Here's another question, right? Very similar, right? This says, in a sense, 3 raised to what power equals 70? Now, folks, that is a little tougher question, right? We might be aware of, right? We might be aware of very specific logarithms. For instance, we would know 3 to the second power is 9, 3 to the third power is 27, 3 to the fourth power may give us 81, but 3 to what power gives us 70, right? All our math has told us is that that's somewhere between 3 and 4 in value, right? 3 to the third power is 27. 3 to the fourth power is 81. So we must take 3 to some number's power, right? To some power where that number is somewhere between the values of 3 and 4. If the result we're looking for that to equal is somewhere between 27 and 81 in value, that being this value is 70. All right? Now, we could think long and hard about that, and we might, really strain our brain trying to figure that out, where in a lot of cases you're going to just have to rely on a calculator, folks. All right? We can use our calculators to also calculate these values. All right? The way we're going to use our calculator here, folks, if we bring our calculator over, you will notice your calculator, let me quit that out, right? Your calculator, right, does involve 2 buttons on it. The log button, right, where we can take a log of a number, and it involves the ln button, where we can take the ln of a number. Now, the ln, if we think about the ln, just a quick note on the ln of x. The ln of x is what we call the log base e of x. All e is called the natural number. All right? It's a number that's a lot like pi in the sense that it is approximated as some decimal. It is a symbol used to represent this irrational decimal, where that irrational decimal in this case for e is what? 2.72 in value. E is about 2.72 in value. E is actually a number we encounter when looking at natural growth. When something is growing naturally, it's either illustrating a natural logarithmic growth, or it might be illustrating a natural exponential growth, right? Or even in the case of growth, we might be considering something naturally happening in a case for natural decay, either natural exponential decay or natural logarithmic decay. All right? That would all involve this natural number e, right, when looking at these cases. And we've seen this e appear whenever we're looking at some sort of constant growth or decay happening, right? You might think about things that constantly grow or constantly decay. You might think of a radioactive element shows constant decay over its lifetime, right? Constant exponential decay. Or maybe the growth rate of a human over time might illustrate a natural logarithmic growth, right? A growth that starts off very quick to begin with, but levels off over time. That might be more of a natural exponential growth, right? A natural logarithmic growth, right? Something may be represented by this logarithm here, right? So on our calculator, we do have two buttons. We have the log button and we have the ln button. The log button, and I should have maybe made note of this too, when we see that log button, that is just a log of base 10 of x. So on our calculator, we really only have two helpful buttons, or some of you might have a bit more fancy calculator that actually has a log of any base button. But for many of us, we may be just sitting around with a calculator that can only calculate logs of base 10 or logs of base e using one of the buttons here on the face of the calculator. You may not necessarily have a calculator that has a button that will let you calculate the log of base 5. All right? How we would handle a logarithm on our calculator that has some other base than 5, if you go back and you recall in the notes, what we rely on is what's called the change of base formula. Right? If I wanted to do the log base 5 of 125 on my calculator, I don't need that under there, right? If I wanted to do the log base 5 of 125 on my calculator, I don't have that button on my calculator. All I have is a log base 10 or a log base e. So the way I take advantage of those buttons is I use what's called a change of base formula. That says this logarithm here can actually be rewritten as the log of 125 divided by the log of 5. Right? Where this base on the logarithm can be any base I want it to be. I can let it be a base 10, where that's what this log button helps me calculate on my calculator. Or I can make it the ln and take the ln of 125 over the ln of 5. Either one of them works. You can actually use any base you want if you reorganize this logarithm into one of these forms or into this format here. All right? And you can see that will be the result we get on our calculator here. If I go back on my calculator and I think about using my log button, I should be able to take the log of 125 and divide that by the log of 5, and it tell me what would be the log base 5 of 125, which we know equals 3, right? And it does give me that result of 3. Same thing would come if I use the ln button. If I hit the ln of 125 and I divide by the ln of 3, not the ln of 3, the ln of what? The ln of 25 divided by the ln of 5. Sorry about that. Right? And actually, I don't need the double parentheses there. Right? Hit enter on that, and then that gives me the value of 3. All right? So, if I'm back here, in this case, looking at the log base 3 is 70, and asking myself x 3 to what power of x equals 70, that can be answered using the log button on my calculator by putting in the value the log of 70 divided by the log of 3. Or I could do the ln of 70 divided by the ln of 3. Either will give me the exact same result. Right? If I do the log of 70 divided by the log of 3, right? That's going to be the answer. 3 raised to what power gives me 70? Well, it's this number 3.867147023. It's this, what appears to be this irrational value, this number, this decimal, that goes on forever and doesn't seem to have really a repetition of pattern in it. At least not from what we can see. Right? This is the value of this x, right, where we can raise 3 to this power, given by this, decimal that seems to go on forever, that will produce the value of 70. All right? We could take note of that. 3 raised to the power. I use the caret key to do our power. And then if I did the minus has an answer. We can bring back the answer here. So 3 raised to that previous answer gives me the value of 70. All right? To concisely correctly to write this answer, to exactly write this answer, this is what the logarithm does. The log base 3 of 70 is the precise way, the exact number, represented by this decimal approximation. It's the exact number that when I raise 3 to that power, it equals the value of 70. Right? In fact, you can see that in the properties. If you take 3 and raise that to the power of 3, log base 3 is 70. Well, what does a log and a power of 3 do to each other? Is they undo each other's algebra. They are those inverse functions of one another, and the result there is the value of 70. All right? This is all logarithmic behavior, folks, and here what it means to be specific logarithmic values. Right? If we had to take and make a table of values for a logarithm, right? Maybe I have the log base 2 of x is equal to my function, and I wanted to make a table of values for this function. At 0 it doesn't exist. X has to be greater than 0, right? Remember from our domain. So I maybe would start at something like 1, right? What's the log base 2 of 1? Well, that's 0. 2 raised to the 0 power equals 1. Well, what's 2? That's the log base 2 of 2. 2 raised to what power gives you 2? Well, that's 1. 2 to the first power equals 2. Well, what about 3? Log base 2 of 3 says 2 raised to what power gives you 3? Now that one you might need to think about, right? You know if it was 4, the log base 2 of 4 says, 2 to what power gives you 4? Well, that's 2. The number we're looking here for 3 is somewhere between 1 and 2. It's exactly this number. We could approximate it using our calculator, right? That is just the value given by the log of 3 divided by the log of 2 on our calculator, right? And it's this decimal approximation, about 1.585 in value, right? If I take 2 and raise it to the power of that answer, I do get the value of 3. Right? This is something we want to take note on so that we can actually fill in a table of values if need be on our calculator for one of these logarithmic functions, right? We need to be able to evaluate logarithms, and that's a skill we don't quite yet have, and that I just covered with you, right? We do want to come back and look at a couple more properties of logarithms, but we'll do that in the next section of the video here, folks. We got to answer question number 6 off of this example key, and then come back to some of these over number 7. But those will be some quick notes, folks, and examples, and we'll work through those when I return. See you in just a few. All right, college algebra folks, last few problems just have to do a little bit with what's presented in 5.4 material, and that is some properties of logarithms. You want to go through that set of notes found up on Blackboard. Those are, there's a few properties there related to exponential and logarithmic functions that you're going to want to take note on. that are going to help you when it comes time now for solving logarithmic and exponential equations. We've seen above how to work with evaluating them, all right, somewhat with our calculator and somewhat relying on our understanding of what is a logarithm, right? This understanding of what it means to be a logarithm. What we're now going to have to consider, or our last section of notes before the test is going to consider, is actually solving logarithmic and exponential equations. Some of that might require some use of properties, folks. So here we have a couple of properties, right? Here, and what the properties can often be used to do is to rewrite or simplify expressions within the equations that we're going to have to solve. So here we're asked to simplify these two equations. And these do happen to simplify rather nicely, right? Both of these play off of the idea that an exponential and a logarithmic expression, when combined or composed with one another, as we see here or here, undo each other's arithmetic. There is a fundamental rule that says if you have b raised to the log base b of m, the result is just the value of m. In a sense, the base b and the log base b cancel, leaving you with just the result of m. And that is what we use right here. 6 log base of 6, those cancel, leaving behind just the value of 5. We also see a similar statement for this side, related to what this expression over here that comes from this fundamental property of logarithms that states, furthermore, if we saw something like the log base b of b raised to the nth power, that this is also just equal to the value of m, right? The log base b and this base b involved in this power will cancel, leaving behind just the power. So over here in this logarithm, this log base 8 will cancel with this power of 8, leaving behind just this quantity x minus 3 in value. So you can see how those two statements simplified by using these properties of logarithmic expressions. All right? And then you have a couple of properties that help you work through problems like this, some of these skills here, where you can take a sum or difference of logarithms and can consider combining them into one logarithmic statement. For example, if I go down here and we might be able to fit that in right up here. If we were to say, for instance, we had the log base b of m, and we added that to the log base b of n, right? Actually, I probably should put these down here. We have the log base b of m. We're going to add that to the log base b of n. And what the rule says is that you can write that as a single logarithm if you multiply the two arguments, if you write it as m times n. Similarly, you could have a difference of two logarithms, all right? And a difference of two logarithms can be rewritten as a single logarithm involving that base of b if you divide the arguments of the logarithm. Since m is the first value in this difference and n is the log base n is being subtracted from that log base m, it is in this order m divided by n. The order of a subtraction is important just as is the order of a quotient. So this order of subtraction produces this order of the quotient. And then the last key rule that we see happening here is if I take an n times a log base b of m, a number times a logarithm can be rewritten as the log base b of that value m raised to the power of n. That product of with a number with a logarithm, that number being multiplied out in front can be brought up as a exponent on the value of n there. We can use those ideas here and here to simplify these statements. To begin with here, we would notice these both involve a log base 4. However, this one has this number 6 out in front of that logarithm. In order to use this property, I have to have just the number 1 out in front of these two properties. So what I apply here is this third property, which allows me to bring that 6 up and make it a power on the value of x. This, in a sense, is going to become the log base 4 of x minus 1 plus the log base 4 of x to the 6th power, where I can now apply this first property and combine those into a single logarithm by writing it as the log base 4 of the quantity x minus 1 times x to the 6th. You could even expand that inside of that logarithm and say here we have the log base 4 of x to the 7th minus x to the 6th if we wanted. All right? Both of those would be expressing the above statement as a single logarithmic expression. Something similar could be done down here. These two constant multiples out in front, the 4 and really I should highlight the 2, can be brought up as powers on these arguments. This is log base 9 of x to the 4th minus log base 9 of the quantity x plus 3 squared. Where since these both involve the exact same base in the logarithm and we're looking at a difference, we can apply this difference property and write this as a single logarithm where this is now the log base 9 of what is going to be the x to the 4th value divided by this quantity x plus 3 squared. Right? These are all equivalent statements along the way here, right? This is equivalent to this, but in what we would say is being expressed as a single expression of a logarithm, or a single logarithmic expression here, folks. And these problems just involved working with these three properties seen down below here, right? And these properties are covered back in the Blackboard notes again, folks, along with a few other useful properties. But that does end our examples over this section of material. Again, we're going to come back to kind of wrap up the chapter material, chapter 5, as we are going to look at the cases for solving exponential and logarithmic equations. And these properties, these skills that we've seen develop throughout these last couple of examples, or last few examples, are certainly going to help us out in solving some of these equations. So, folks, we'll be back to see that in the next video. But this does wrap up examples for sections 5.3 and 5.4 material. All right, so the next section we will see is going to be over section 5.5, just looking at solving exponential and logarithmic equations. I'll see you then.